trying to think if there's been anything really profound in science since we last recorded that has really struck you.
I heard about one thing that was portrayed as a big breakthrough, and I think it is to a point, but it's important to understand it. So it was about nuclear fusion.
Okay.
Maybe you've heard about it because it was in the USA at a research lab. And for a nuclear fusion, you have basically different kind of ideas how to achieve it on Earth, because it's happening in stars or in the sun, in the core, but it's really difficult to do it on Earth because you need extreme temperatures to be able to do it, and also sometimes extreme pressure. So there are different ideas how you can do it.
Okay.
At Garching, at the campus Garching, where I'm studying, there is research fusion reactor with a tokamak design, which is a design for a fusion reactor from the Soviet Union, and it is quite old. It's from the 60s, I think. And the basic idea is that you just heat the stuff that you want to fuse together up really. You just make it really hot, and then you get a plasma, and you have to confine the plasma somehow because it's really hot. There's no material that could withstand the heat. It's I think about 150 million degrees Celsius, which would be, I think in Fahrenheit, it would be about the same. Maybe it would be more, I would guess. But so more than 100 million. I guess it's not important if it's 100 million or 500 million. It's really hot. And then you confine it with a magnetic field.
Okay.
And then you can extract the energy. So and then fusion is happening, which makes it even hotter. And then you can extract the energy through neutrons that bounce on the walls and heat up the walls. And then you, with the generic power plant, then you just heat up water and drive it through turbines. And that's how you can generate electricity. And that's there's another idea, which is the stellarator, which is similar but has some minor differences. How you can find the plasma in a torus is the shape, which is basically a donut. So torus is just the mathematical term for donut. And yes, that's one idea, and there are a lot of them. What means a lot of them? There are a few in Germany. There's one, I think the biggest now is in UK, and they build a really big one in France right now. And it's a project with countries from all around the world, which I think is really interesting that they unite for one project. So there's the European Union, USA, Russia, China, Japan, South Korea, India, and a few more. And that's the biggest one that they want to build, and that's that should be the first one that produces more energy than you bring in.
That's the whole goal of.
That's the whole goal, yes.
Energy, right?
Yeah. So all of them right now need more energy than you get out of them.
Okay.
If you even get something out of them, because for example, for the one in Garching, they don't have a system to extract the energy. They just want to create the plasma and make research on the plasma. And there are also other ideas. And the main ideas that I heard about was with lasers. And that's where the breakthrough was in the USA. Because and there are a few ideas how you can do it with lasers. But the one where the breakthrough was is it's kind of that you have a cylinder. And inside of the cylinder, you have a chamber where you want to produce the plasma, and then you have a really strong laser, and the laser comes from above and from below, from all kinds of angles, and that's what makes it possible makes the creation of a plasma inside of the cylinder possible. And for the first time, I think it was in January or in December, so not long ago, they were able to prove that there was more energy created than the laser brought into into the chamber. So they had an energy excess. I think it was 2 megajoule went into the chamber with the laser, and then the plasma emitted 3 megajoules of energy. So 50% more than you brought in.
And so the reason why this is all important is because the 21st century is going to take a lot of energy to live our lives and run the world, right? So we're trying to find different innovative ways where we can get more energy out than we put in, right?
Yes, and as I'm thinking about is that kind of nuclear fusion is more or less the holy grail of energy, because if it's possible, then it's a really nice way of producing energy, or not producing, but making energy usable, because you don't produce energy per se. Because you have a lot of the advantages from nuclear fission, like carbon emissions or something like this, and you don't need that much of material to be able to get energy. But you don't have the drawback of radioactivity, because the elements that you use are so low radioactive that sometimes it only takes about weeks or so that the radioactivity is gone. And most of the time you don't even have to think about it, because it's also so confined. And also one really important thing is that with nuclear fission, you have to cool the thing down, and you have to extract neutrons so that you don't have a uncontrollable exponential reaction, which is basically the nuclear bomb. Which would happen if you just let it sit there and do its thing. But with nuclear fusion, if you don't do anything, then it just cools down and nothing happens, because you have to create the extreme environment. And if it's not able to sustain itself, then it just cools down. So that's the worst thing basically that could happen, that it cools down and you don't get any energy. But there's no real threat of a nuclear disaster. So,
that sounds pretty sweet.
Yeah, if it would be possible, it's I think the estimates are about 2040s, 2030s maybe, that you could do it. And also there's if it's really applicable in a large scale, then I think the humanity don't have to worry about energy for the next thousands of years, because you basically just need water, or especially an isotope of hydrogen and lithium. But you can also produce lithium or beryllium. I'm not sure about it. And there are also different kinds of reaction that you could do. But you can basically also generate one of the things while it's operating. So I think it was about 1 gram or so that you need to fill the whole reactor in the research reactor that it was in. So you need, I think, only a few kilograms per year to run the power plant, which is, compared to coal, really nothing. Because I think you need thousands of tons to run a power plant for a year. But for a fusion reactor, you'd only need a few kilograms.